So I think it's nice to look at several cases in terms of light intensity. Now, first of all, when we talk about the intensity of light, one of the most natural kinds of measures that might seem reasonable to us, especially for engineering people, is a radiometric measure, which is based on energy. And what's instead used when we talk about perception of light, when we talk about light in the context of human vision, we use what are called photometric measures, which take into account human sensitivity to light by wavelengths, which is exactly related to these photoreceptor sensitivity plots that I showed you, right. So there are measures that take this into account, and that's what we will use, photometric measures rather than raw physics. Does that make sense? Because the visible spectrum is special only to us, right, and many other animals, but the visible spectrum for other animals changes quite a bit as well. For example, there are some birds that have photoreceptors that can measure ultraviolet light, and then they end up with beautiful patterns on their wings that are in the ultraviolet spectrum, and they can see that. So for them, that's the visible spectrum. So if the birds were making measures, these particular birds, they would use something different, but this photometric units are based on humans, and I will use just a common unit here of luminance called candelas, which is based on the light, roughly speaking, is based on the light emanating from a candle. So I will use candelas per meter squared as a unit of radiating light. And I just want to give some examples, which these appear in the Mather textbook, and a lot of the surrounding concepts of what I'm talking about here also appear in there in chapter 6. Let's look at the right here, luminance, and how many photons per receptor. Receptor. How many photons land in a single receptor at a certain level of luminance. And I will just give some cases here. Paper in starlight as the weakest. So we're outside, there's no moon in the sky, there are no clouds, just stars, and you hold out a piece of paper, and I assume you're not near the city or anything like that, right. So imagine it's very, very dark, you just have a piece of paper. This corresponds, and of course it's hard to reproduce this exactly, but this corresponds roughly to, I think this table is nice for comparative purposes. This corresponds roughly to 0.0003 candelas per meter squared, which in terms of photons hitting your photoreceptor, you will get about 0.01 per second. So not very much, just maybe barely above some noise threshold if you're lucky. So that's the lowest end. And then we have paper in moonlight. This goes up to 0.2, and you get about 1 photon per receptor. So I just want to illustrate the enormous range over which your photoreceptors seem to be useful. Looking at a computer monitor, this is about 63 candelas. Of course, it depends on a lot of factors, but then you get 100 photons per photoreceptor. Room light, which of course again there's variation here, but 316. and it's about 1,000. Blue sky. So looking up at the blue sky, I'm about 2,500. Sure, it depends on where you're at in the world. And finally, paper in direct sunlight. So if you sit outside, imagine here in Chennai sitting outside trying to read a book or something, perfect white paper hitting the sunlight. That's very, very bright. So paper in sunlight which gets up to 100,000. So that's quite a range when you look at it. I like this photons per receptor idea, this concept. And so going from 0.01 up to 100,000 per receptor. So at that point they get very, very saturated. I lived in Finland for a while, and I think of snow blindness too as well, right? You have this, remember we talked about the reflectance of snow last time, and so you can imagine snow in sunlight extremely bright. So, maybe a few of you haven't seen snow in sunlight before, I'm not sure. So, let's see, someday you'll see that if you haven't. Okay. So one thing I want to talk about is because of the way rods and cones are divided up and they have different functions, we end up with two different kinds of vision modes. One is called scotopic vision. I'm going to write it on the other side of the board because I'm afraid I'm running out of space over there. So scotopic vision. And the other one is called photopic vision. So these are two different modes of vision operation that we have. Two different kind of modes that our vision systems get into. The dominant photoreceptors. So if you want to add the word dominant, they're dominant photoreceptors. For scotopic vision are the rods, and the dominant photoreceptors for photopic vision are the cones. And for light levels, typical light levels for scotopic vision are less than 0.01 candelas per meter squared, and photopic is greater than 10 candelas per meter squared. Of course, there's some intermediate regions, so there's a gradual transition from one to the other in actuality, but the extremes are very clear what's going on. So as far as color perception goes, when you're in scotopic vision mode, it's monochromatic. And in photopic mode, it's trichromatic based on the RGB sensitivities of your cones. So trichromatic. And there's the adaptation period. In order to switch modes, it takes about 35 minutes to go fully into scotopic vision mode. This seems reasonable, right? So if someone shines some bright lights or you've been around the light for a long time, you go outside, how long does it take before you can see really well in the dark, right? Maybe after a few minutes you're already improving, but if you want to get completely into scotopic mode, about half an hour. If you've ever done some work with telescopes trying to look at the stars at night, it takes quite a while before you can really see everything perfectly, about half an hour. Going in the other direction, it's about 10 minutes to adjust. Pupil dilation is also a significant part of this as well, right? So when you're in a scotopic vision mode, your pupils are dilated, taking in as much light as possible. So this is also another adjustment the eye is doing, yet another degree of freedom in the optical system, right? Roughly speaking, 90% of our of our neurons are devoted towards photopic vision. So that means we are daytime animals. Maybe that's no surprise, right? We're not owls or bats or something like that. So, so we're basically designed to survive, to do the things we need to do to survive during daytime, and then we're a lot more vulnerable at night, right? But not completely vulnerable thanks to scotopic vision. So we have like 10% dedication to that.